computer. Awesome.
Might need to be a co-host. No, I got it now.
Okay, perfect. Welcome, everyone. This is another fun session with Deep Learning Adventures. We're fun and engaging a community with members all around the country, all around the world. I want to thank everyone for joining us tonight, especially my great friends and co-hosts, Dmitri, David, and Robert, as well as friends from all around the country. Again, if this is your first time, welcome. I want to make sure that you feel welcomed and you join our future sessions. I'll quickly share some information about our community and where can you find more about us. So you can find about us more on Meetup under Deep Learning Adventures. We have been on a series of what we call data science and deep learning adventures. And on our YouTube channel that I will share with you in the chat, you can see more about it. Our latest adventure was a specialization from Coursera called Tensorflow Data and Deployment. We learned a lot of interesting concepts there, including training and inference on the browser, on edge devices, as well as advanced TensorFlow topics like data sets and how to do optimized data pipelines and so forth. We had a fun capstone project last time we did a custom face detection project. We also deployed it on our phones where it would detect each one of us as George, David, or Robert. We had a custom training set as well. We've covered Kaggle courses in the past, and I just noticed today that Kaggle released a brand new mini course that we'll hopefully cover at some point on time series and machine learning for time series. From time to time, we also have guest speakers, and we have a list of guest speakers coming up hopefully soon that share their industry expertise as well as projects they're working on. So again, thanks everyone for joining us, and this will be a fun adventure. So today we're going to talk about tension and transformers, and Dmitri has led this initiative, and I want to thank him. And Dmitri and Robert will lead us through this first part series. This is a two-part series. Today we're going to talk about some of the basics of transformers and attention models, and next week we're going to cover some more advanced topics. So with that said, welcome again, and let me stop sharing and hand it over to Dmitri.
Thank you, George. So let me share my screen. Sorry about that. Yep, here we are.
Perfect. Yep, we can see your presentation.
Yep, cool. So thank you, George, for this opportunity. This will be a two-series event, today and next Wednesday. So today, what we're going to cover is we're going to go briefly over the history of transformers, how they came about, and what they do. Then we will go a little deeper into the this very important paper when actually the first transformer was described, which is called "Attention is All You Need" by the Google Brain team. Then we will cover the math inside the transformer, and more specifically the query key value math in a visual blog by Jay Alamar, which is a wonderful resource, and Jay has a lot more visual blogs covering different aspects of deep learning, so I highly recommend it. And then finally, we'll go through a specific TensorFlow implementation of a classical transformer, which is available on the TensorFlow website, which specifically does a neural machine translation from Portuguese to English. So we'll look how it's structured, and actually, if we have time, do some training. So this is the plan for today. So let's just quickly let me go through what transformers are. So basically, depending on how much background you have in RNNs and non-transformer models, this may or may not be very familiar to you. Basically, as other language models, transformers build some representation of the input tokens. So different language models do that with different efficiency depending on the task at hand. So transformers became very powerful and very very efficient and at many NLP tasks because they build representations of each token given the entire context of the input sequence. So for example, the input sentence may be 20 word long, or actually 500 word long, if that's a paragraph of the text. And if we want each word to be sort of aware of the entire context from the first token to the last token, that's where the transformers actually shine. And so that proved to be a very winning sort of strategy and approach for many tasks. It started with machine translation, but quickly proved to be very state-of-the-art efficient for things like text summarization, entailment, grammatically correct, the recognizing grammatically correct sentences, etc., etc. So below, I brought the top 10 winning teams and models from the GLUE benchmark, which has, I believe, about 12 or 10 different types of NLP tasks. And as you can see, so all of the top 10 are actually based on transformer architecture. So all of these are transformers. Many of them are variants of the famous BERT, which we will cover next week. Apart from being a general model that allows, as I said, each token to look, so to speak, at the entire context, a couple more points I want to make is they allow for parallel training in contrast with sequential RNNs, which need to sort of wait until the last token has been processed to process the current one. The transformers don't have that limitation, and so everything can be trained in parallel. Also, one more thing, there is a wonderful resource called Hugging Face, which actually provides wrappers and APIs to virtually every transformer out there, both for TensorFlow and PyTorch. So it's open source and widely available. So with that, let me go to the next slide, which is we try to this is a sketchy timeline. This is not comprehensive by any means. It's just the few key milestones that that basically shape the transformer journey. It seems that they've been forever, but they're relatively new, like 5-6 years old. In 2015, it was the first paper that introduced attention as such for machine translation specifically. And then in 2017 came out this paper by Google, which is the paper that we're gonna dissect today, which is called "Attention is All You Need." They introduced the transformer term for the first time in the paper. And then around 2017, 2018, Hugging Face began publishing and putting in open source all of the wonderful models that they have. In 2019, the BERT came about, which we're going to cover next time. BERT is a giant transformer with many different optimizations and interesting training sort of objective. Proved to be state of the art for many different types of NLP tasks, and still as we saw, like for today, for today's challenges, it's still BERT or its variations that appear to be constantly winning. The Facebook published another variant of BERT called Roberta, which was like a giant optimization ablation study for BERT. There was XLNet. The OpenAI team published GPT-2, which was not based on the BERT architecture, but still a big transformer. And of course, we all of us have seen the GPT-3. So these wonderful models that are able to generate arbitrary text, it seems, which came about like last year. I was going to mention that TF Hub, TensorFlow Hub, has BERT and its variants. I believe about 20 of them just out there for download as TF Hub models, which also was like I think they uploaded last year, and it doesn't stop actually. Since BERT, this 2019 was probably the most prolific year, because since then, basically the space exploded, and there are literally dozens of variants of BERT and the smaller ones. And just this year, Google Switch and Microsoft NVIDIA published the Megatron paper. So these are also transformers, just the only difference is that they are the giant ones. I mean, there are many differences, but to give you like a perspective, BERT had about 100 million parameters. GPT-3, if I'm not mistaken, about 100, about a 500 billion, and Google Switch is over 1 trillion parameters. So this is, we are already in the territory where people think about the carbon footprint and all of that from the training. But they still keep beating the previous generation. So size seems to pay off in this race so far. So we'll see how it develops. So with this historical introduction, let me briefly go to the attention mechanism itself. So it was, as I said, introduced in 2015, specifically for neural machine translation objective. And let's just take some time, just go through that and make sure that we really understand attention, because the later papers and the general transformer architecture is based on the attention as one of the central elements of its architecture. So before attention came about, the machine translation specifically was relying on RNN architecture in this upper left corner, which basically process the input sequence one by one. So these are the tokens, and generated an arbitrary number of hidden layers on top of it through basically matrix multiplication plus some nonlinearity. And so they created this hidden representation of the tokens as they processed it. And so even in this input processing stage, we can see that it's essentially sequential. So there is no way we can jump from one token to the other. So at the end of this input processing, what the classical architecture does, it creates basically one vector which was also called a thought vector, right? So the general representation of the entire input sequence. And then this part, the blue part, was called the encoder, which basically encoded the input sequence into this giant vector. And then the decoder, which is this brown part, decoded that thought vector, which is, let's say, a French sentence, decoded into English, and the loss will flow from comparing the potential tokens, the potential translated tokens with the ground truth. And so the loss will flow from this XYZ down through the network. So that was the whole architecture. A fairly simple one, although people used advanced RNNs such as LSTMs, etc. But it didn't help the basic bottleneck, which was the need to crump the entire long sequence into one thought vector. So that was the limitation. Technically, there was another sort of or related limitation that stemmed from the gradients having to pass through too many stages of the same matrix. Remember, these transitions from left to right are not actually different matrices, so those are the same transformations. And so basically, depending on the structure of this matrix, the gradients that were flowing forward and backward could explode or shrink to zero. And so in both cases, that actually hampered training. And so you had to be really careful in initializing the weights, and all kinds of problems with vanishing gradients. So in 2015, these people came with an idea of actually bypassing this sequential nature and letting the output token, which is this HT. So the HT and HT is actually the output token, look at the entire input sequence, regardless of where they are in the output positions. And so that was a very innovative and groundbreaking way of looking at things. And so it quickly caught attention and got very good scores at all kinds of machine translation competitions. But basically, what it does is the attention weights, technically speaking. So we train not only a representation of we train not only the matrix of actually taking the hidden states of the input and producing some output, but also in parallel we're training a special matrix called attention weights, which tell us which words of the input are most relevant to the current token that I'm trying to produce. And so it turns out that depending on the actual input tokens, the attention can be spread differently. And so for example, in this particular example, on the right, the European Economic Area in English would translate into specific words in French in the opposite order, right? So the Zone Économique Européenne, which is the opposite order, and there is no way, unless you're doing rule-based sort of heuristics, there is no way to learn that per se automatically. That those are the relevant spots to look at, so to speak, unless you put that through attention-like mechanism, and so let the engine to learn that mapping automatically. And so this was as I said, a groundbreaking technology, and attention in transformers is actually taking this and slightly modifying in terms of the implementation, but that doesn't really change the way the attention is conceptualized. So it's conceptually doing the same thing. So mapping the input to the output. So that was 2015. And please stop me along the way if you have any questions. In 2017, this paper came out, which was called "Attention is All You Need," which basically claimed that you don't even need the recurrent architecture to be able to map the inputs to the outputs. You can do that if you would imagine with a big square matrix of the inputs and the outputs. This is a sequence of the inputs and the outputs, and have them look at all of them, basically to each other, which is O(n) squared time complexity, where n is the sequence length. But still, this is parallelizable because we don't have to wait until the previous token has computed. We can just train all of the tokens in both sequences in parallel. And so I think that was the one of the key sort of drivers for transformers to get traction, because that now they are amenable to parallel training and parallel computation. And so on the right side, it's basically the structure that we will be implementing later today in the notebook. But this is the key structure in this paper. Attention is all you need. So it has the encoder and the decoder part. So encoder is on the left and decoder is on the right. So both encoder and decoder have the attention mechanism. Attention is actually this, three-headed arrows are all attentions, all of these. And I hope, we will cover this in the visual blog by J. Alomar. But basically, conceptually, the self-attention is making sense, helping the engine make sense of the input sequence as such. Like even before you think about translating English to Portuguese, what does the English sequence say? And or in our terms, what is the correct representation of the input tokens of the English sequence itself? And so we would look at things like which adjective we should look at, which noun, or which pronoun is corresponding to which noun again. And so all of these complex, syntactical relationships that are out there, are described by the self-attention without before even considering, translating to other language. And so this is taken care by this, self-attention head. And then, each layer has, except for the self-attention, it has a few other elements, such as, the residual connection, and then, there is a small feed-forward network, and a few dropouts and normalization layers, etc. But the key is this, the attention that looks, that lets basically the sequence learn from itself. So this is the encoder block, and we will be describing this in more detail when we go through the actual notebook. Now with the decoder part, the decoder is trying to take those hidden representations of English input, for example, and produce the Portuguese output. And what it does is basically, first, it actually also learns from itself. And so this is another self-attention head that looks at the generated Portuguese sequences so far. And then when we need to generate the next token, what we do is we actually ask the input English sequence through a basically, there is a separate mechanism that takes queries, keys, and value pairs, the three of them. And so the queries would come from the Portuguese token, and keys and values would come from the English input, and then they will produce, they will combine, and basically the Portuguese query will ask, so what is the most relevant sort of meaning from the English input that I need to be translating now? And so that is an interpretation, but essentially what it does is basically finding the most relevant output, so the most relevant Portuguese token given the English input and all of the Portuguese tokens that were produced so far. So I know it might be a little hard to follow this verbally, and I hope once we go through the actual notebook, it will become clear. But yeah, so it's also followed by a feed-forward part, and also through by some residual connections and normalization. And all of this is considered one layer. Now, layers can be repeated arbitrary number of times. In our case, they repeated, I think, 4 times. So in BERT, for example, they repeated 6 times. So this is a largely hyperparameter that we can tune. So yeah, this is the encoder decoder part. Now there are a few other things that I want to mention before we turn to the JLMR's blog. So the first thing is that the paper that we will implement, that they look at the multi-head attention. So it's not just one sort of attention matrix that looks for correspondences between the inputs and outputs. We split that into arbitrary number of heads, so to speak. And so what it does is basically lets different parts, different types of heads look at different types of relationships. For example, if the dimension of our input space is, say, 512, which we'll be implementing, so basically, each token has a dimension of 512. Then we could split that 512 into, say, 4 parts or 8 parts, and then each attention head would look at specific portion, 1/8 of that the dimension, and say, for example, this attention head would look for semantic correspondences between the two the inputs and the outputs. This attention head will look for say some syntax, some other types of features that may be relevant for the translation. And so in other words, we would basically avoid the situation when all of the attention for the entire 512 dimension of the output will be centered into one word. So one word could look sort of with different eyes, with different heads, could look at different parts of the input sequence and find those different parts relevant. So this multi-head thing was again very instrumental in improving the quality. And so final detail that I was going to mention is the positional encoding. So which we will also be implementing in the notebook. What they introduced in this paper is this idea that because this is not an RNN, we don't have like an intrinsic understanding of what comes after what. And so, there is this giant matrix, but we need some idea of the relative and absolute positions of the tokens. And so what they came up with is some clever way of actually adding some some values that correspond to position of the token in the sequence. So whether it's that the first, the second, etc. And that allowed the attention heads to understand whether the tokens are next to each other or apart from each other, whether the tokens are closer to the beginning of the sentence or to the end of the sentence. And that actually helped, again, the final metric, the output quality, by a great degree. So this positional encoding was also very clever sort of trick that they introduced. So in the interest of time, I think I would probably stop here. George, let me see if there are any questions on this part, and then we'll move to Jay Alamar's blog, and then I want to leave some more time for the Tensorflow Notebook.
Right.
There are 2 questions that were just posted to the chat, and I certainly won't give a complete answer, but I think we'll get a start at answering both of those questions during the next section.
Okay. Can I ask a clarification question? So this NX number that you're mentioning here, this multiple layers, and I like the way that you described it, Dmitri, where you said that maybe one is looking at syntax, maybe another one is looking at something different. Are they sequential? Are they in parallel, these NX layers?
So these are sequential, so they build on top of each other. So for example, if you had 2, so the bottom layer would produce some representations of the input sequence, and then the next layer would actually feed off the those representations. So those are sequential. And yeah, so but the multi-head is actually this little thing inside, and so each of those sequential layers will have the multi-head capability. And
Right.
so different parts of a transformer looking at different parts of the input dimension. So those will be working in parallel, not sequential. So.
Got it. Thank you. And just to clarify, in the previous slide where you were mentioning different, this is in the attention slide, yeah. So the way that you calculate this context vector and this align weight, so there are 2 famous papers there by Bannon and Wong, and they slightly different how they define this context vector. Is that just, is there any major difference, or is that just a mathematical representation of this attention mechanism?
I don't remember the specifics. So I think the attention vectors, they can look at the entire sequence, which would be maybe those are the 2 variants that you described. So that is, I would say, the most complete one, and more like the actual transformer that we'll be working with. But computational less efficient because it's O(n) squared. The other thing that you can do is you can say that only my immediate neighbors are important for me. And so in self-attention, I would not look for the entire sequence. I would also only limit my attention to ±2, say, or ±3. And then it becomes not O(n) squared, but O(n) actually. And so I think that those were the key considerations. But I think those are important considerations in the sequential context, because sequential doesn't let you do parallel computations. with the attention with the transformer architecture, it seems that people sort of let go of this local attention idea and just look at the entire sequence. It's just a matter of compute and the resources they have.
Right. And final question, in the slide number 2, you mentioned different models. I guess they differ on how on the previous slide, on how deep your transformer architecture is, how many layers you have in the transformers, slide number 2.
Oh, here?
Yeah.
Yeah, so I looked at a few of them. Actually, I worked with T5 in my previous work. So Ernie is a Chinese language, for example, transformer. So they must be, differences that describe why certain transformers are good at some tasks but not the others. So this score is a composite score composed of like around a dozen different tasks, and so some engines might be good at text summarization but not like, for example, question answering. And so there is the link over here, and so I encourage you just to go check which ones perform better. It seems that the Baidu and Chinese people actually put a lot of effort into this, so it has become a multi-million-dollar investment line for many of these teams.
Right. Cool. Thank you, Dmitri. Any other questions from anyone in the chat or live?
Yeah, I had a question, George. This is Adrian. Yeah, going back to slide 5 and the questions on spatial versus sequential, I guess the opportunity is there to parallelize. What is your experience or insights do you have in the work that's been done to try to do distributed deployment of this in parallel hardware? Is that the right section to focus on, the multi-head? Or are there other dimensions of this structure that are more likely to be used to partition distribution?
You mean at the inference time or training?
Inference specifically, deployment.
I can't answer that question. So I would probably we could speculate and do interpretations, but with the training it's clear. With the inference, I don't know. I think so. The one thing that I could comment on is that the multi-head is happening within the transformers. So it's basically the transform itself takes in the entire vector, like D model, whatever you have, the depth of the model, and then inside the transformer it splits, calculates, and then concatenates back. And so that's like, if we think about implementation, that is within one class actually happening inside it. So maybe that's one of the reasons that's not a good place to distribute along that dimension. So but maybe there are some clever implementations that would allow for that.
Yeah, thank you.
Cool.
All right, let me stop sharing.
Yep. Thank you, Dmitri. That was super useful. And I think we head over to Robert, correct? Awesome.
See, first I need to figure out how to unmute. Now I can figure out how to share the screen.
All right.
Eventually we'll get something on. Okay, you can see my screen now?
Yes.
Cool. So we are going to briefly very briefly look at the attention mechanism to get a little bit more intuition as to what it's doing. And I have to say that of all the big concepts that I've encountered within deep learning since I got into it and started trying to read papers, discovering attention is probably one of the most difficult topics. Just, I don't know if it's the papers themselves or just the topic or what, but I found that I couldn't understand any of the papers I was trying to read. I needed to dive in and find more basic resources. And this blog post here by Jay Alomar is a great place to start. I'm going to actually show another resource as well here. But so we are looking right now at the Illustrated Transformer. Let's see if I can move the zoom image out of the way. Okay, get to the top of the page. This is the Illustrated Transformer. Jay Alomar posted this in the summer, I think, of 2018. And it was just a few weeks after he had posted another much shorter post about attention, this visualizing neural machine translation, where we're talking about that same paper that Dmitri just showed this figure from. And I think looking at this figure is helpful to get some intuition of what's going on, right? Each word, at each element of an output sequence, you are trying to see which element of the input sequence is most predictive of the word that we need in the next sequence for this machine translation task. So you can see that as we saw earlier, we have a pretty good match here. The attention mechanism is finding which word it should be looking at in the other language. This also illustrates, you can see that we have an entire matrix here of elements though. And this is actually what's going on. What can be parallelized here is the fact that what we really need to do is compute every single element of this matrix. What is the attention between each pair of words, which leads to this O(n) squared computation. But it has a number of huge advantages, which is why transformers and the attention mechanism have basically won out over RNNs, at least in the world of really high power computing at the most resourced places, such as the Googles of the world. So there are a number of advantages, but I'd say the real advantages that the attention buys you is not only this ability to parallelize, so you can take advantage of GPU hardware and other highly parallelized architectures. You also have this issue in the RNNs about being unable to, for really long sentences, you might not be able to, the context vector might not be able to contain enough information. If you have one long sentence with many, many clauses, it might not be able to refer back to the correct word in the beginning of the sentence if there's a pronoun for which that is needed. You also do help to take care of this issue with vanishing gradients, as Dmitri mentioned earlier, because you have smaller networks. So let's get back over here to this one. And this is a long look at the topic, a great read, highly recommend. We're not going to touch but a very small portion of it here. And the very small portion that we're going to touch is this part here once we get down to self-attention at a high level. And then we'll be looking at the details here with the vectors and matrix math. And again, just like I had trouble understanding the papers at the beginning, I would say that the first time I read this blog, I was thoroughly confused as well. I think it takes many sources to elucidate this material, and I'll share with you all one that I found super helpful. May not be super well known, but it's a YouTube channel actually by a professor at University of Waterloo in Canada. And I don't know if anyone here has seen this channel, but there's a couple of playlists. He teaches reinforcement learning. I guess he taught these sections. but the one of interest here is really this intro to machine learning. And what I found helpful about this course was that it is painstakingly thorough, but really goes down into the weeds to explain things that in many cases the details are glossed over. So the lecture from which I'll share a little bit of content, or at least my own transcription of the content from the lecture. It's a course for, I think, upper level undergrads, lower level graduate students, but it's really the very comprehensive machine learning course. We're looking at lecture 19 here on attention and transformer networks. I have actually viewed most of these lectures now because I was pretty impressed with what I found in the transformers part and realized that I wanted to bone up on things that I hadn't seen in years too, like support vector machines, and which are covered in just as much detail. So highly recommend this channel. I'll drop a link in the chat when I'm done speaking. But every one of these lectures is very detailed, and a lot of, you can see in the little thumbnails here, he draws on the board, actually does equations, solves problems, very simple problems to illustrate the concepts. I found that incredibly helpful. So what are we actually looking at here with the illustrated transformer? We have these queries, keys, and values. And the fact that they're given these names is possibly indicative of another analogy that we can draw. And in particular, key value stores, where you might have a database with items, values that are archived in the database, and we need to access them by keys, and we are going to send in a query and hope that that query matches one of the keys in order to pick out the value that we want. So for a simple example of something like that, this little NoSQL tutorial here gives a very simple example. So you might have a phone directory where the key is someone's name and the value is the phone number. So how does this relate to attention and this idea of being able to find words across a spectrum here? So what we have in attention is we're going to have keys, and we're going to have a query coming in, but the query is not really going to match a key, right? In the phone directory, if we try to search for Mark, say without the O on the end, then we want it to come up empty because Mark is not listed here. However, for the attention mechanism, if we're going to search a query for something that's very close to one of our keys, we do want to find it. So we want to do this. The attention mechanism is at its heart a bit of a fuzzy query matching machine. So what it's going to do, compare the query to the key and do some computation, try to find some similarity between them, and then return some value that is a function of the similarities it found. So one of the diagrams that the professor draws on the board in the YouTube course, I actually just scribbled down on paper and we'll share that now. Can you see this little image here?
Yes.
Okay. So we may have a sequence, an input sequence, say the keys down here. This may be each word in the sentence, key 1, key 2, key 3, key 4. And we are attempting to match it to some query. This may be coming from the decoder if you're talking about a transformer here. But what we need to do first of all is determine some measure of similarity between the query and the key. And the queries and keys are both some vector of a certain number of dimensions. Typically, you'll have them be some fraction of the embedding dimension. So the embedding dimension for your transformer may be 512, for example, and you may have 8 attention heads. as was described earlier in a multi-headed attention. So you might have 64 be the dimension of each of these things. And then you will end up, after doing these attention computations, calculate the concatenation across all the heads. But in this diagram, we're just looking at a single head to try to make sense of this thing. So we're going to calculate from these key vectors and query vectors some kind of similarity score. And it's a function of the query and each individual key. And the most naive way to do this, you might consider, by the way, you can see my little cursor across the screen too that I'm trying to use as a pointer.
Yeah.
Okay.
Product, yeah.
Not super visible on my screen, but if it's coming through, that's cool.
I like the analog touch today.
What was that?
I like the analog touch today, the notebook.
Whatever works. So the query dot product with a key might be the most naive way to do it, simplest way to conduct a similarity calculation between a query and a key. Another alternative, you might divide by some scalar factor, scale it by the dimension or the square root of the dimension. This might help the values not to grow over time. And the third alternative here is to have some W matrix in the middle that is essentially going to project the queries into a different it's a vector operation. You're taking one vector and projecting it into a different direction to try to match the keys. And it's a good question to think about why might you want to have the query vector projected in a different direction. And the example offered in the lecture that I showed earlier was an example. Suppose you're looking at a question answering dataset, such as the SQUAD dataset, Stanford Question Answering Dataset, I think is what that stands for. And your query might be a question, and the keys are all possible answers to that question. And there's no reason a priori that one might necessarily expect the question to have the exact same embedding as the key. In fact, that would be kind of weird if it did, because then that would mean that you already know the answer in the question without having to look anything up. So, not to mention that embedding vectors probably contain other information about grammar, such as whether or not there is a question mark at the end of the sentence. That might be part of your embedding as well. So you can think of this W here as just some intermediate matrix that is going to project the queries into some other space to better match the keys. This is trained during the training process. This is trainable weights matrix. Once we choose this similarity, and we'll be doing this projected one here with the W in the real attention mechanism, we get similarities here. And then the similarities, of course, are not necessarily normalized. So we do this softmax computation here to make sure that the attentions computed here, which are also scalars, are going to sum up to 1. And then we're just going to take this linear combination of the values. So you can think of it as being, you looked up somebody's name in that phone book, you found the people whose names were closely matched to that one, and you're returning some linear combination of their phone numbers. Not a practical use for a phone book per se, but an analogy that might help us to understand the attention mechanism. So back to the transformer blog. I'm just going to go through this very quickly, because I realize we could spend hours on it, as I have spent hours trying to study this stuff. So we're going to look at the top of the self-attention at a high level. And this is another interesting example of why we might need attention. The animal didn't cross the street because it was too tired. What is the it referring to? Remember, the it may need to go back any number of sentences or words within the sentence. In this case, you might think, oh, well, the animal is the subject of the sentence and it is the subject of the sentence, so of course it is referring to the animal. But what if the word, maybe we could change it to the animal didn't cross the street because it was too hot? We've just changed one word there, and is the hot referring to the body heat of the animal? Maybe the animal thinks that the street is hot because the asphalt's been baking in the sun all day and doesn't want to burn his paws. Or maybe in the English language, we tend to use "it was" with words like cold and hot without actually the "it" referring to anything specific, right? It's just, it's hot out. So getting down to the detail here, this is a slightly more detailed version of the hand scribbling bit that we saw on the previous page, where now we're looking at dimensions of these vectors. So we'll have words coming in such as thinking and machines. These are words from the sentence you're trying to match. They have a particular embedding. The queries here are typically much smaller embedding than the native embedding. This is drawn here as 4 and 3 just to be something so that we can make sure that the matrix math makes sense, but usually it'll be some integer multiple such as 512 and 64. You'll have a different matrix for WQ, the WK, and WV, each of them transforming this embedding dimension down to the space of the keys, queries, and values. So the second step here is calculating a score. That's really the same thing as the similarity score that we saw in the previous diagram. Calculating the self-attention, we need to calculate some kind of score, and here they're showing the score as a dot product, and effectively the dot product already has this weighted matrix in the middle because of the W's that we put in the previous chart. Then rescaling here, dividing by 8. This is to combat the vanishing exploding gradient problem, make sure that we're at the same basic numerical spread in each layer. And the softmax step that we saw to get the attention A coefficients away from the S coefficients of similarities. And then we multiply each value vector by the softmax score. That is what we see up here. The multiplications up here, attention value, and the summation of AI, which are scalars, times VI, which are these value vectors. And once we sum them up, that concludes the self-attention calculation. And then we're going to send that along to the feed-forward neural network that is within each attention block within the transformer. Any questions on this part so far? I see there's a few things in the chat.
I love the fuzzy logic or fuzzy matching analogy that you made, and some kind of weighted average of the phone numbers. I'll remember that. That's an interesting explanation. Yeah, and Ted gave basically a summary of the notation that you had in the notebook, which I really like as well.
Yeah, he says, the way I think of self-attention, the queries and keys calculate the similarity score, and we return the weighted average of the values using those similarity scores as weights. Yeah, that's pretty much it.
Any questions, comments from anyone? The other resource that I posted is just using attention mechanism in the RNN world. How long sequences are harder to model and decode. Basically, the longer the sequence is, the harder it is for the model to keep attention, and it's easy to lose focus. So you can see the image that I shared, that after a while, the attention just drops. The model doesn't know the final words, where do they refer to. So in your sentence, it crossed because it was too hot. It probably lost its meaning. It wouldn't know where to refer.
Yeah.
Hey, Robert, can I add a comment about sort of what attention does?
Yes, please.
Um, so the thing I wanted to add is that your tokens, your words, they have this numeric embedding. So let's say it's a 300 length vector or whatever it is. Okay. If you have two words like animal and it, if you ignore the fact that there's actually positional encodings in BERT, if you just look at the base encoding for the word animal, the coding for the word it, right? They will always have the same similarity score, no matter where those two words appear in the sentence. They could be the first two words, they could be the last two words, or like in the sentence that you showed, animals near the beginning and it's near the end. Okay, so I know that the mechanics of the math of the transformer is sometimes difficult to understand exactly what's happening. But the property that I think is important to understand is that animal and it will get a certain score. Let's say a fairly high score, right? Animal and it will get a fairly high score no matter where the words appear. So it doesn't matter if you change the sentence from saying the animal to saying the brown animal, the small animal, the very, very, very large animal, right? You're changing the position of things, but the nice property with transformers, it'll never change the similarity score between those two words. Okay, so that's effectively what the transformer does is it takes you from a world where you're looking at how far away are the words from each other to the actual content of the words. Just the meaning, the content of the words. And so if you don't understand the math, that's the key thing that the transformer does. So any sentence you have animal and it, and the reason why you need like multiple heads and multiple layers is that you can imagine like there are sentences where it shouldn't refer to the animal. You need other things that your model is going to take into account other than just this very basic similarity score. So I don't know if that's helpful for some people, but I thought I would just throw that out as a sort of separate from the math. Like, so what does that really mean? What does it bias?
Yeah. Now, at the same time, you are training the weights, right? So at any given time, that similarity score will change between any two words.
Yeah, so you need to train it to have really good weights. But once you have a certain set of weights, so let's just say at inference time now for simplicity, so the model's frozen, okay? Any sentence with the word animal and the word it, and those words could even appear multiple times in that sentence, they will have the exact same similarity score between each animal and each occurrence of it, because at this point, right, it's the weights are frozen, so you have a particular query associated with animal, you have a particular key associated with it, and they will always compute the same score.
So as a counterexample here, so in the example that Robert showed, right, the animal didn't cross the street because it was too tired, versus the animal didn't cross the street because it was too dangerous. In one case, it refers to the animal, but in the second case, it refers to the street. Is that, I mean, I would expect that the weights would be different on each case.
So the similarity score between animal and it will be identical in both cases. However, the scores between, say, hot and street, or no, what was, was it tired? Sorry, between tired and street versus dangerous and street, right? Tired probably has a low similarity score compared to street, but dangerous might, and tired has a higher score with animal, and dangerous might also, but that's the reason why a single layer transformer can't really do everything, because in one layer, all it's really doing is just this pairwise words, and it needs to then kind of, so in computer vision, right, you sort of think of like you start with small details like vertical lines and diagonal lines. And then eventually you say, oh, I have circles and I have triangles and I have, this is an eye shape, a nose shape, whatever, right? You get bigger and bigger features. I don't know if this is literally right, but essentially as you go up in layers, you're getting bigger features. And so then you're sort of saying, oh, okay, there's this idea of animal and street and, you know, and so then at some point it needs to then say, I predict that tired has a, you know, a linkage with the animal in this case, but dangerous would have a linkage with, you know, the street.
So the similarity score between it and animal, you're saying, is like the analogy of the Sobel filter, the first layer in a computer vision.
That's right. So when you're doing dogs and cats, something in the first layer that's looking for vertical lines and something in the second layer that's looking for circles, let's say, they're still looking for verticals and lines and circles. They really don't know if it's a dog or a cat yet. You need to kind of get the much bigger context before you say, you know what, I think this is a dog, right? So in this case, the attention, the similarity score between animal and it in that very first layer, it's going to be the same, no matter what adjective you stick at the end. Now the whole weighted average will be ever so slightly different because you're also averaging in the effect of that adjective, the tired or the dangerous at the very end. So it will slightly change it, but for the most part, yeah. And that first layer, it's not really going to be able to do that. It's just going to directly tie, you know, that pronoun to that noun. I think what's the right word, the antecedent, you know, whatever, right? So you would hope that at the higher levels, as you're stacking these transformers, then you sort of talk about like subjects and verbs and, you know, objects and or whatever, you know, it might not be literally that way, but that eventually it's sort of figuring out these bigger objects of meaning. And then at some point there, the attention is going to say, hey, wait a second, you know, this tired doesn't really make sense for a street. It kind of should connect with the subject, the animal in this case.
So one thing that I've always found helpful with computer vision is some of these visualizations where you can see the spread of a particular element of the kernel or one pixel and how it affects various elements, different layers down. You can see kind of the communication between pixels, if you will. I wonder if there's any such visualization like that for text, right? Where you can see these simple relationships at the first layer and more complicated context in later layers. Have you seen any
Yeah,
or something like that?
Doesn't Jay have it later? If you scroll down, some different examples where there's multiple heads and they're looking at different things.
Yeah, the one you're actually showing.
Is actually showing the different layers of the.
Okay, so here
if
you
I
can
can,
sort of see it. All right, sorry, go ahead, Vivu.
Go ahead.
yeah, if I can pop in for a second. So Ted, some of the stuff you were saying with like picking up different similarities between words at different layers, I think something that I'm not sure if I was hearing it wrong or if we're kind of mixing it up. So there's a difference between multiple transformer layers and multiple heads on the attention mechanism. So there's different types of attention. There's like causal attention, which is self-attention. There's multi-headed attention. There's different ways where you can structure your attention layers where like you can only look backwards. But when it comes to multi-headed attention, the more layers you have, you don't really run into that problem of we're starting to pick apart like which word is like a pronoun and that. But that's something that we see more with stacking transformer layers. So it's not like the multiple heads of attention. There are actually a lot of papers out that when they structure their transformer networks, they'll like actually talk about the number of heads they did in their attention layers, which type of attention layers, and they don't really notice any what's the word? There's like no there's no problems caused by adding more heads. It just kind of decays off and they don't see any benefits. Whereas the opposite is true when it comes to adding more and more transformer layers. So let's say we have a model like BERT with like its 8 transformer layers stacked on top of each other. one of the problems that comes up is a lot of the BERT tasks are more just for natural language understanding as opposed to like actual tasks that you would want to do. So towards the end, like the last couple layers of the BERT model, they start generalizing towards the problems that you sort of described, where it's trying to get really picky and pick apart like, oh, this word should always fill in this gap, or this pronoun comes 3 times after an adverb. And we start to run into those problems. So there are a couple like resources I'll try to link in a bit that will break down different layers of transformers. So like some models that'll have 8, 10, 6 transformer layers, we can actually break down at each level, look at how it's actually like making these embeddings and where the decay starts to happen. And when it comes to actually using these things in practice, even like common libraries, like Hugging Face libraries, you can choose to often not use the last transformer layer because you'll often get better results picking like the 7th one or a couple layers before messing around there. But the main point that I'm trying to get at is that if you're trying to understand transformers and attention, there's a difference between stacking multiple transformer layers and stacking more heads when it comes to multi-headed attention. There typically isn't like degradation from multiple heads, but there is from adding more and more transformer layers. So typically multi-head is good. We don't see problems there other than wasted resources and a decay, but adding more and more transfer layers, you see the problem, you see the model really generalize towards one solution, and it's not really the solution you want. So that's kind of a distinction that should be made.
Yeah, that's really cool stuff, Vibu. Yeah, I was actually trying to get to something more basic. So again, when we talk about CNNs, we talk about that like the early layers might be looking for things like lines and circles or textures, right? Now, again, this is a conceptual model. I'm not saying that that particular trained CNN is literally using a Sobel filter and looking for vertical lines, right? But that's the way we think of it, is as these sort of simpler shapes, and then it builds up. So I'm not saying that the BERT model is literally exactly doing this, but I'm saying that in that first layer, once you train it and it has a certain key and a certain query, matrix that's been trained, anytime you see animal and it in the same sentence, the similarity score is going to be, roughly the same. And again, I'm also glossing over, there are positional encodings, so it's not true that it's exactly the same, but just for ease of understanding, if you simplify an RNN, you could say that, well, what an RNN does is it places half the weight on the previous word, a quarter of the weight on the word 2 words ago, an eighth of the weight the word 3 words ago. That's very different, because then if you move around the word animal, the weight is going to get, how much emphasis it puts on the word animal is going to differ just by virtue of it appearing somewhere else in the sentence with a simple RNN. That's the only thing I was really trying to say, is that the breakthrough of the transformer is that it'll give the same weight between it and animal no matter where the word appears. So simply adding an extra adverb or slowly, or in the middle of a sentence, really doesn't change the way a transformer connects words.
Cool.
Yeah, the only thing I would also add is that there seems to be added value from stacking the layers on top of the others. So there is going something similar to hierarchical extraction, such as in CNNs. And so that's why I think, especially at these earliest stages, this was more art than science, and, remains so to this day largely. And so they actually tried different structures. And so this 4 or 6 or 8 layers on top of the others was just proving to be extracting the most that there was, to extract. So with that, let me share my screen and try to quickly go over the TensorFlow Notebook. in the interest of time, because I think we have only about 20-25 minutes left, I will go through some sections rather quickly. So the notebook itself is on the TensorFlow website, and I should probably show where it is. Oops. TensorFlow. Yeah. So on TensorFlow text, there is these 3 sections. The first is about text generation with RNNs, a very cool notebook. The next one is sequence to sequence with attention, basically implementing the early neural machine translation paper that we discussed. And this one is what we're going to go through. This is a transformer model for language understanding. It's a really cool section as a whole. So let me go through the setup. So basically, there is this Portuguese to English data set from TensorFlow datasets, which is TFDS. And again, please check it out. There are like tons of datasets. This one is convenient because it's a relatively small one. There are only, if I'm not mistaken, about 50,000 training examples, and so I was hoping to do French to English, but it was like 30 million examples, so it would take forever to train. So this one is relatively small. So what we first do is we download the data set, and then we can actually look at the pairs so separately. And I don't speak Portuguese, unfortunately. So, but these are the training examples. As you see, they're already slightly processed, not lemmatized, etc. But they're lowercase and the punctuation is separated, etc., etc. So there has been some processing already done in the TFDS. Now, the first, and again, I mean, it would be interesting to actually dive into the TFDS and see what other corpora are there, etc. But we just don't have time for that. So they also do have a prepared tokenizer, which is based on byte pair encoding. So again, they prepare that both for the English and Portuguese. In case we don't have it ready, there are lots of resources, including on the TensorFlow website, where you can, at least for an English, you can download. BERT has its own tokenizer that was basically trained together with BERT. So we're just going to use the off-the-shelf one. So the tokenizers have these methods. They have a lot more. They're just we're showing everything that is not a dunder method. So the tokenize, detokenize, and the vocab. By the way, the vocab attribute would give you just the entire vocabulary that the tokenizer uses. So this is actually how we process the English input through the English tokenizer. So converting this actual English phrase into a set of tokens. This is not necessarily whole words, right? So there may be, like phonemes or combinations of symbols based on whether the word has made it into the byte pair encoding frequency or not. So for long words, for example, this is the we can see how it looks. like, you know, the basic words such as and, when, etc. It's of course like a separate token, but then, you know, search ability is split into two, because the ability is also a frequent sort of ending within, you know, all kinds of words. So that's why, you know, it splits into two. There is actually quite some discussion about whether this type of byte pair encoding is actually preserving some syntactic meaning, and therefore not completely sort of randomly, you know, chopping the words into different pieces. Although they will have, the byte pair encodings will also have just single characters as the lower level, sort of lowest level recourse. You know, if it's a completely unknown word, it will split into individual symbols. So that's with the tokenizer. And then, yeah, we will basically, what we will need is to prepare a data set that is ready to push into the training pipeline pairs of English and Portuguese, both for the training and validation purposes. And so this is what it does. Basically, you know, the batch size is 64, and you know, this is very, very small, right? But because the structure is so heavy that even for a GPU, you know, one epoch would take about what was that, about maybe, you know, 2 minutes or something. So this is even this relatively small data set of 50,000 examples would train for about like 40 minutes or so. So to prepare the data set, we cache it, shuffle it, batch it into batch sizes, and then we map this tokenization function onto all of them. Basically, you know, process each example into tokenized sort of pair of tokenized outputs, and then we'll basically call these make batches onto the train examples and validation examples. And I forgot the split. I think they split 2080 or 1090. Anyway, it was somewhere above, yeah. So this is the first actual part of the encoder and decoder or the transformer that is actually implemented. So the positional encoding, again, without going into much detail. So what it does, it assigns a different value for a different sequence, the different position in the sequence, and different position in the feature vector. And so, you know, well, let's say the embeddings of the tokens get embedded into 512 dimension, and then depending on where you are along that D model, which is called D model here, so along this feature dimension, and where you are along the sequence dimension, you get assigned a different number from 0 to 1, which is basically your positional encoding. Now, they did actually, this is quite simple. If we had time, we would go over what exactly they do. What they produce is basically a simple function, something like this. And so what it does, my interpretation of what it does is actually it's able to compare, you know, words that are next to each other, that are 2 apart from each other, 3 apart from each other, etc. So these are the periodic patterns from here. If we need to, if there is a meaning to be extracted from the position encoding, being, say, for example, 3 from each other, we can do that. But also there are parts of the feature vector that are not dependent on the position. And I think this was also discussed in the paper. So they kept it intentional. So parts of the feature vector are context dependent and other parts are not context dependent. And so if the transformer needs to, it can just learn general global sort of representations of or global mappings of two words, regardless of whether they appear next to each other. And so this is what they add to each token. And so again, there was some discussion about whether adding actually makes sense. So in this specific paper, they did add it, but in some other realizations, implementations, they concatenate the positional encoding to the embedding dimension to make it sort of to let them learn the pure position as opposed to the encoding plus position. So another important element is masking, and someone mentioned the causal masking. So basically what it does is, you know, in the pure encoder-decoder architecture, so in the classical encoder-decoder architecture, the encoder is fully transparent to everything. So, you know, from any part of encoder, you can look into any other part of encoder, and from any part of decoder, you can look at the encoder in its entirety. So encoder is open to anyone, and so for that reason, you know, the masking that we have to do is only to let the transformer know which tokens are padded, like, you know, the 0 tokens don't look there because they are just artificially added to the sequence. So that's the only masking or padding that we do on the encoder side. On the decoder side, we need a causal mask, which is, you know, don't look at anything that is from yourself and to the right, right? So only look to whatever precedes you. And so that's why we need, for the decoder part, we need a triangular diagonal mask to make sure that we can only look at the you know, at the preceding tokens. So this is what they do, how it's implemented. So we will see basically later what they do is they replace the mask itself maps the tokens to zeros and ones, and ones are the actual missing or forbidden tokens that we can't look at, because later in the scaled attention, the ones will get multiplied by some very large number, and then, you know, the softmax, or, you know, the negative infinity, and then the softmax will squash them back to 0. And so basically the ones in the mask are finally going to tell us that you know, in the softmax, these mask tokens will get the weights of 0, and so we will not take them into account. So what they do is they create the padded and the look ahead masks, so the triangular masks, and then they implement this key concept that Robert described, so the dot product attention. So let me just again very quickly reiterate a couple points. So the Q and K are actually having the same sequence length, and so you know, I have it here. Yeah. So when they get multiplied along the you know, the D model dimension, and so when they get multiplied, the dimensions that get that are you know, that survive are basically the dimension of the sequence of the query and the dimension of the sequence of the key. And so dimension of the sequence of the key is the same as the dimension of the sequence of the value. And so basically, as a result of this, we get the output dimension is basically, the values times the sequence of the query. And so values here are just they're not considered part of this attention thing. So this softmaxed QK is actually the attention weights, which we'll be able to see how they actually look. So this is how they implement the scale.project attention. So they first multiply the Q times K, and each of them have the batch dimension, and then the sequence length, and then the depth. The depth is the demodel, or demodel divided by the number of heads. It depends. Yeah, so the first step is multiplying these two together, this Q and K. So this is what we do, because we need to have this transpose B true, because we need to bring the depth into the second to the last position for them to basically work. And then what we do is we divide it by the square root of the demodel, and then we add to that the scaled attention logic. So the mask, as I said, is 0 and 1, and so when we add to that the this is like a negative billion, so we add to the logics, so to the raw inputs before softmaxing, we add like a negative billion to whatever we don't want to take into account, so we don't want to pay attention. And so this is how the masking works, because then so basically after adding the masks, then we take the softmax, which by the way has just the direct implementation in TensorFlow tf.nn.softmax. And so after doing this, our output dimension is sequence length of K and sequence length of Q. So these are the attention weights that we can see, and this scale.product attention, this method outputs them for us to be able to inspect visually. But also, of course, the key sort of intention of this module is to produce the output, which is multiplying the attention weights by the V. And as you can see, V enters the play only at the very last stage, so it's not part of the attention itself. Let me pause right there. Are there any questions with this implementation?
No, I just found the examples after this block of code very, very useful, FYI. Yeah, then here we can actually see how the scale.product attention works. And what they have is, these are the keys. These are just arbitrary numbers. This is a matrix of keys. So exactly as you described, Robert. So, the key value pairs, first of all, that they have to be, they have to have the same leading dimension, but the internal dimensions can be different. For example, we have 4x3 and 4x2, and then the query, for example, the query we have is, what they try is this 0, 10, 0. So what we do is we look through the keys, because we look at the correspondence between the queries and the keys. We look through the keys, we find the most matching, or the closest matching to the query, which is the second one. And so because of that,
we will output the second value as the output of this whole implementation. And so that's exactly what happens. So, you know, the attention weights are 0, 1, 0, 0, right? So 0, 1, 0, 0. So the entire attention is here, and the output tensor is 10, 0, which is this one. And so you could imagine if these are of course a lot of zeros, but if in a general case, you know, there will be a softmax mechanism that actually sharpens our attention to the one position that is the closest to what we're trying to find. So if this would be, say, I don't know, 191, then, you know, we would have a probability distribution that would place, you know, the predominantly the mass will be here on the second element, but then, you know, slightly you would still have a little weight in the other positions too. And so, yeah, I guess that's what they do. That they try 0, 0, 10. Again, 0, 0, 10 is spread evenly between these two keys. And so that's why we will get, you know, basically a weighted average of these two values as an output. And let's see if that happens. Yeah. So, you know, attention is spread evenly, and we will get, you know, the weighted average of the two values. And so I guess, you know, this is very interesting to play with if you if we really want to, you know, dive into how this QKV mechanism works. And so one last thing, probably before adjourning until next Wednesday, is I'll go through the multi-head attention. And so that they actually discuss why they have the multi-head capability, what it does, and then they actually implement it here. So what they do is they divide the entire D model into a number of heads, and, you know, we should make sure that it divides evenly. And then what they do is they create basically separate shards, you would say, for each of these chunks of the model. And so, you know, splitting is basically done with the same TF reshape as you would typically reshape a NumPy vector. Is just we create an additional fourth dimension. So it's going to be batch size, sequence length, the head, and the short feature vector. And so, you know, instead of 512, you would have, if this is 8, you would have 64. And so you would have 4 dimensions. And so then perform scale dot product attention on each of these 4 vectors, like this. And so the scale dot product attention, the method itself is capable of digesting a separate dimension, actually any number of dimensions. And so this method doesn't care if we have another dimension or not. But then, you know, after doing that, we have to concatenate them back together into one long 512. And so, you know, this is what we do. This is what we do here. Just again, reshaping it into batch size. So basically crumping the number of heads and the small D model into the big D model. So this is what we do. And yes,
Hey, Dmitri?
so yeah,
Can I just make a quick comment here?
sure.
So every implementation of Transformer I've seen does exactly what you just showed, but I just wanted to comment that for learning purposes, it would be a lot easier to understand this code if, when you say you have 4 heads, if it created 4 separate objects and then you saw it looping through those objects and calculating attention separately 4 times, right? But for efficiency purposes, they never implement it that way.
Right.
They figure out a way to do this more complex matrix multiplication that actually does the 4 separate matrix multiplications all in one fell swoop. And so when you're reading the code, I always found that that's that one piece that makes it a little bit hard to read, especially if you don't know the math, to understand that, yeah, this is actually a trick that just does multiple matrix multiplications at the same time.
Yeah, I guess this is for efficiency purposes only. I agree with you. It would be more transparent if we just looped through the heads. That's true. Yeah. So and I spent some time. Actually, I implemented this. We will probably have some time to talk about this next time. So I implemented about this structure in a non-NLP context, and so I had to actually go through all of these permutations and all of that, and so spend some time actually understanding what's happening. Yeah, so you're absolutely right, Ted. So yeah, but coming back to one of the previous comments, so maybe this can be distributed at the inference time, sharded into different sort of heads operating independently. It's just they would operate on shards of the internal dimension, and so maybe it's possible to do that and then concatenate on a on a separate worker back together. But in this particular case, it's just in one class that does all of that in one go, basically, both splitting and then concatenating back. George, I'll leave it up to you. So we might actually gallop through the rest of the notebook, or leave it until next Wednesday. Let's discuss, what would be the best approach.
Sure. I know you have a time limit as well. Yeah, I appreciate it. Okay, so let's pause here. We have the link for this notebook as well. We can take a closer look. But basically, this is building the transformer architecture that you showed us, Dmitri, from scratch, like component by component.
Yeah.
And
it actually does. Although we trained only for whatever, like 40 minutes, it does a pretty good job at translating and figuring out the attentions, as far as I can tell, for English Portuguese pairs. So it's actually working. It's not just a template.
Right.
In this case.
Okay. Maybe next time we can briefly touch base on this if anybody has any questions. But yeah, we can look at this notebook on our own.
Last thing I was going to mention is what was interesting to me is that they implement here the gradient tape, and so the lowest possible level you can go with TensorFlow in training the network. And so if we have time, depending on the next time, so we might want to spend 5 minutes just I would go through how they structure it and what you can do within that training step, because you can do pretty much everything. Create your own loss functions, any type of custom metrics, etc., etc. So it's really very, very flexible, and so they do that. They also implement something which is probably reminiscent of TensorFlow 1. So they create a computational graph in memory to speed up the training process. So I thought that was also interesting. So there are interesting pieces here and there, apart from the transformer itself, that are probably worth touching on next time.
Awesome. Thank you, Dmitri. We really appreciate it. This is a very thorough notebook. So yeah, we'll definitely take a closer look independently. And next week when we get together, maybe we can spend like a few minutes in the beginning if you have any questions or feedback.
Thanks for the presentations, by the way.
Cool. Thank you, everyone. Yeah, people appreciate it. Thanks for your comments. And if you find any resources, feel free to post them on our meetup event page. Yeah, I can post the links as well. All the links that we used are on our meetup page here. the presentation, the notebook that Dmitri went over, the blog post that Robert went over, and I'll also post the new links that Robert shared with me, or any other links you share. Cool, friends, I appreciate it. I know we're hitting the 2-limit hour here, and this is one of our longest sessions as well, and one of the most interesting as well. So I really want to thank you for sticking with us, and thank you, Dmitri, and thank you, Robert, for leading these sessions, and thank you everyone for joining us with your questions. Just wrapping up here, next week we'll do our part 2 of our Transformer series. As Dmitri mentioned, we'll cover some basic transformer models that are based on this architecture that we just covered today, as well as hopefully go through another notebook and look at some NLP as well as some non-NLP applications of transformers. And the recording will also be available hopefully tomorrow. We have a new playlist for attention and transformers here as well. Awesome. With that said, thank you everyone for joining us. I'll stop the recording here. Feel free to hang out if you want. If you have any questions, comments, feedback, but I'll just stop the recording at this point. Thanks again.
All right, thanks.